These are my example calculations for the lab on the force table. So let's get to the table on the paper that I actually set up my example. So this is, when you watch the video, is what I said, that's what I measured prior to actually doing the video. 495 grams at an angle of 180 degrees, 235 grams. I'm sorry, this keeps coming in there. 235 grams at an angle of 270 degrees, and then this is what I measured while I did the video, 175 grams at an angle of 0 degrees. So I'm going to calculate the force, that is the weight, once I have hung them on the strings and let them hang over the edges of the table. So it's going to be 495 grams divided by 1,000 to get it kilograms, and then times the acceleration due to gravity, which is 9.8. So that comes out to around at 4.9 newtons. Okay, and 235 divided by 1,000 times 9.8 comes out to 2.3 newtons. And I'm going to keep it here in two significant figures because, as you notice here in my grams, it's basically just two significant figures, with the last one being an estimate halfway between, in this case, 490 and 500. That's the best accuracy the spring scale can give me anyway. So that's why I keep my weights right here at two significant figures. And 175 times divided by 1,000 times 9.8 should come out to 170, and I'm sorry, 1.7 newtons, and that's indeed correct. Okay, so these are the data that I have to work with, my example data. And now I'm going to go here. There are four methods that I have to use: the graphical method, the applet, the trigonometric method, and the measured method. So let's see, I'm going to start out with the graphical method. It says, for each setup you need two drawings on each Cartesian graph paper. In the upper half, make a large enough drawing in the XY coordinate system and draw in the force vectors emanating from a single point. In the lower half, make a second drawing with the same vectors tip to tail. Pay attention to each vector keeps its length and direction. Measure the magnitude and the angle of the net force. I kind of skipped this one here. I use small ring. When you watch my video, you can see that instead of using a small ring, I actually just used a knot. I knotted the strings together. Okay, this is the graphical method. Okay, I'm going to choose a single point here with something. There we go. There, that could be the ring that I actually didn't use. And I'll put it here, say. And then I'm gonna measure at, let's see, 180 degrees, which is to the left, 4.9 newtons. So 4.9 newtons would be this much. There we go. And there we go. Then I measured at 270 degrees, 235 grams. Uh, 2.3 newtons, that is. So 2.3 newtons. Kind of looks like there. There. Okay. And then I measured at 0 degrees, 1.7 newtons. And that is my first drawing. So looking down at the table, one weight is pulling this direction, another one this way, another one this way, and then of course I have my counter force acting on it. Okay, the second drawing is you would draw these again, tip to tail, that is. And here what I'm going to do actually is I have the luxury that I can move these around. So what I'm going to do is I just copy them. Sorry that I'm a little lazy here. You would have to redraw them, but that's no big deal. Let's see. Oh, there it is. Okay. Okay, so I would grab one of the three, it actually doesn't matter which one of them, and put it down. Now I put another one, and I put it tip to tail. And it looks like I have to move this a little bit on the screen. And then I take the third one, and I move it tip to tail. And as I said, any kind of order would actually work. I could have started out with this one. I can show you. Oh, hold on, let me actually show you that this is the gap here. This is the net force from the original tail to the final tip. Kind of remember that's what it is. And if I turn these around, some kind of other order, for example, I would start out with this one here, continue with this one, and end with this one. Notice that from the original tail to the final tip, it's again the same one that I just drew a moment ago, or that I pointed out a moment ago. Okay, the net force, therefore, I'm going to change the color on this one here, make it green. This here would be, therefore, the net force. In this direction, the entire assembly is pulling, and I kind of can see it with this large vector over here, that probably the whole assembly wants to take off in this direction here. Okay, this one here, I'm going to measure how much it is. And again, you would have to redraw them a second time yourself, but with these right angles, that's no problem at all. And on, I believe, one of the setups, you actually have to turn it a little bit. You have a different kind of angle because you go over a corner, and you would have to use actually a protractor to draw in that correct angle. Okay, anyway, I'm going to come up with, looks like what I drew here is 3.7 newtons. So 3.7 newtons at an angle of, and I have to turn my protractor around, angle of, let's see, this one, I'm going to read 30 plus another 5, looks like 35 degrees past the 180 degree mark, because I have to go from here all the way around, because this one is actually 0 degrees, that is 90 degrees, 180 degrees, 270 degrees, so this one is 35 degrees past 180 degrees, so it's 215 degrees with 3.7 newtons. So that's the graphical method, and this is what you would submit. Actually, I will write it down here. Okay, so that was 3.7 newtons. That looks a little small here. At 215 degrees. That looks a little better. There we go. Okay, so my result, therefore, for my example are the graphical method, 3.7 newtons at an angle of 215 degrees.